Good morning students, welcome to the next lecture of electronic measurements and instrumentation. Today we will see the topic of spectrum analyzer. My name is TSS Nagpavan Kumar. Let us see the concept of spectrum analyzer. First see the definition of spectrum analyzer. A spectrum analyzer measures the magnitude of an input signal versus frequency within the full frequency range of this instrument. So whatever the instrument frequency response you are going to measure, you can measure the complete frequency range of the instrument with its response of magnitude information or amplitude information. So see here once again the definition. A spectrum analyzer measures the magnitude of an input signal versus frequency. The magnitude of the signal or input signal with versus with frequency within the full frequency range of the instrument. So this is the definition of the spectrum analyzer. The primary use to measure the power of the spectrum of known and unknown signals. The primary use of the spectrum analyzer is to measure the power of the spectrum. So whatever the spectrum you are giving, that spectrum power you are going to measure for known and unknown signals. Whatever the known and unknown signals are available, for those signals you are going to be measure the power. Okay, so this is the definition of the measure spectrum analyzer. So coming to that, the spectrum analyzer, how it is differing with a normal oscilloscope or normal CRO. The normal CRO shows the signal's amplitude or magnitude information with respect to the time. Okay, with respect to the time, what is the amplitude of the signal? Okay, so we cannot get the frequency information on the x-axis on this cathode ray oscilloscope. But in the spectrum analyzer, we will get the frequency information, the response of the frequency information we can see on the x-axis. On the y-axis we can see the magnitude information. The spectrum analyzer is little bit costlier with compared to the normal CRO, where the normal CRO is the cost of nearly 16,000 to 50,000 rupees, where digital storage oscilloscopes with the cost of 30,000 to 1 lakh rupees, where the spectrum analyzers they start from the 2 lakhs rupees. So they will start the cost of nearly 2 lakhs of rupees. Okay, right. So this is about the spectrum analyzer. So coming to here, the spectrum analyzer has a lot of applications. For example, see here in this board you can see 4 variety of applications. Okay, first let us see the frequency responses of the signals you can see in the 2 different pictures. So it is showing in the x-axis, nearly in the x-axis it is showing up to 20 Hz to 10,000 Hz. In the y-axis you can see the signal directly in terms of dBs. So the magnitude information you can see on this spectrum analyzer for a given input signal. And see here in this peak, the information you can select the frequency, where the frequency range you want to see, whichever the frequency ranges you want to block, you can block here. And in the left side channel, in the right side channel, or in the both channels, if you want to see signal, how to we have the options to vary that one, and you can refresh the signals for each for every 50 milliseconds of time or every 40 milliseconds of time. You have the option to adjust the time, refreshing time also, and you can see the graph with the maximum information or lines of information, the scale information, the range information, the whole informations you can vary with this spectrum analyzer. And here this is the one method of this is one type of view in the spectrum analyzer, and this is another view of the spectrum analyzer. So finally what we can say, we can see the signal behaviors or their magnitude in y direction, and we can see their frequency information on the x-axis. This is a major purpose of the spectrum analyzer. Spectrum analyzer, lot of applications. For example, coming to that, an audio engineer, for example, in a music recording theater, an audio engineer is monitoring the speaker's information. So when you are speaking loudly, you will get maximum information. That means you can see for high frequency signals, for low frequency signals, you can see the volume magnitude levels, the volume of the magnitude levels and their frequency responses you can see by using different types of spectrum analyzers. So lot of applications are available for the spectrum analyzers. So this type of displays you can get in the generally audio applications. So in the TV channel applications, you can see different types of frequency bands here for the TV, and the audio informations, their magnitude informations. You can see the strength of the voice and the frequency of the voice. Both informations you can see in the spectrum analyzers. So these are the different types of applications of the spectrum analyzer, where you have to monitor the continuous frequency response of the signal. You have to use the spectrum analyzer. Okay, so lot of research applications are completely based on the spectrum analyzers. So these are the very wide variety of spectrum analyzers. So we will see the key points related to the spectrum analyzer. Whatever the key points are there for designing a spectrum analyzer, those points we will see in this class. So let us see the spectrum analyzer. The most common way of observing signals is to display them on the oscilloscope. In the most of the times, we are seeing the signals behavior in the oscilloscopes only, with time as x-axis and y-axis has magnitude information. That is amplitude of the signal versus time. So amplitude versus time we are seeing. This is the time domain. This is the time domain signals. So the CRO can represent only time domain based signals. The oscilloscopes we can use for the representing the time domain signals. Next, it is also useful to display signals in the frequency domain, where the spectrum analyzer is used to display the signals in the frequency domain also. We can see in the time domain signal, we can see frequency domain signal. In the spectrum analyzer, we can see both the time domain and frequency domain signals. The instrument providing this frequency domain view is the spectrum analyzer. So the frequency domain view you can see in the spectrum analyzer. Next, a spectrum analyzer. A spectrum analyzer provides a calibrated graphical display on the CRT. So it is providing a calibrated graphical display. That means it should calculate everything, and it will provide all the information, and it will provides also calibrated information with the frequency on the horizontal axis and amplitude on the vertical axis. In the horizontal axis, it is representing the frequency, and vertical axis it is providing the amplitude information, that is voltages information it is providing. On the x-axis it is providing frequency information. So this is a very important. For as an electronic student, we know the importance of frequency, right? Without knowing any frequency of the signal, we cannot process any information. Okay, right. So this is a basic spectrum analyzer parallel filter with bank analyzer. So see here, this is a parallel filter. This is a parallel filter bank analyzer. So this is a basic concept behind the spectrum analyzer. So here we have the input signal. Here we have different types of filters, and this series of filters is giving the outputs, and the simultaneously you are seeing the output at the CRT display. Simultaneous output to the CRT display, and this information is representing the output graph like this. So this is the filter bank output, which consisting of n filters of information. So this is one filter, this is another filter, this is another filter, this is another filter responses. Each filter responding parallel simultaneously on the graph of this filter. Okay, so see here, this is the basic behavior of the signal. Let us see the theoretical discussion of this diagram. Right. Displayed as vertical lines against these coordinates are sinusoidal components of which the input signal is composed. The height represents the absolute magnitude and the horizontal location represents the frequency. So see here, in this x-axis we are representing the frequency information. The sinusoidal behavior we are observing in the vertical directions in the CRT display. These instruments provides a display of frequency. These instruments provides a display of frequency spectrum over a gain or frequency band. Over the frequency band, it providing the signals behaviors information. Spectrum analyzers use either a parallel filter band or a swept frequency technique. It is using a parallel filter band. Okay, so it is using a parallel filter band, right? Otherwise, it is using a parallel filter band or a swept frequency technique. It is the spectrum analyzer is designed based on these two techniques, either parallel band filter or swept frequency technique. Based on these two availability of the any of the technique, the spectrum analyzers are going to be designed. In a parallel filter bank analyzer, so this is an example of parallel bank filter analyzer. The frequency range is covered by a series of filters whose central frequency and bandwidth so selected that they overlap each other. So wherever the filter bank series of filters we are providing for covering all the entire frequency ranges. Okay, in a parallel filter bank analyzer, the frequency range is covered by a series of filters whose central frequencies and bandwidth are selected that they overlap each other. So almost all by overlapping all the frequency signal, all the filter banks are covering all the signal frequency ranges. Typically, an audio analyzer will have 32 of these filters, each covering 1/3 of unactive. So almost all the filters are covering all the signal frequency ranges. Nearly 32 filters we are generally using in the spectrum analyzer. It covers all the information and it is covering 1/3 of an octave. Next, for wideband narrow resolution analysis, particularly RF or microwave signals, the swept technique is preferred. Particularly in the range of RF and microwave signals, if you want to see for the spectrum analyzer, there is a designing technique we are using, that is a swept technique is used preferred here for RF signals and microwave signals. That is very narrow resolution signals we can see with the help of this swept technique based. Otherwise, we can use the parallel bank series filters. Right. So coming to that, this is a basic spectrum analyzer using swept receiver design. This is a swept technique based spectrum analyzer technique. Previously we have seen the parallel band filter technique. Now we will see the spectrum analyzer with the help of swept technique based. So here we have the input signal. Here we are giving the input signal. Here we have a first stage is a mixer, where the mixer is connecting to the input signal and it has a voltage tuned oscillator. Here we have a VTO, voltage tuned oscillator. In this voltage tuned oscillator, we have the minimum and maximum frequency range of the signals, and this voltage tuned frequency is connected by the sawtooth generator. This is connected by the sawtooth generator. The sawtooth generator is connected to the oscillator, and the sawtooth generator again connected to the display section of the horizontal lines in the spectrum analyzer. How the CRO will be connected in the horizontal and deflection plates, in the same way here also we have horizontal and vertical deflection plates. In this horizontal and vertical deflection plates, the horizontal plates are connected to the sawtooth generator. This is already we know. For any type of display, the sawtooth generator is connected to the horizontal deflection system. One side it is connected to the horizontal deflection system, another side it is connected to the voltage tuned oscillator. This voltage tuned oscillator is connected to the mixer circuit. Next here we have IF stage, intermediate frequency amplifier stage. Next, detector and we have a video amplifier circuit. Here we have a detector and video amplifier circuit. So whatever the frequency signals we have to see, those signals we can detect here perfectly. Detector and we have a video amplifier circuit. With the help of this video amplifier circuit, we can see the signals on the spectrum. We can see the signals on the spectrum. Okay, so this is about the spectrum analyzer block diagram. Let us see the theoretical discussion of this spectrum analyzer. This is a basic spectrum analyzer. Next, the sawtooth wave generator. Here, the sawtooth wave generator provides a sawtooth voltage which drives the horizontal axis element of the scope, and this sawtooth voltage is the frequency control element of the voltage tuned oscillator. So, where this sawtooth generator is control the frequency of the voltage generator circuit, and it is used for displaying the frequency range based horizontal deflection plates, where the normal CRO horizontal deflection plate is connected to the time based generator. Here, the frequency component we have to see on the x-axis. So, for that reason, here we are connecting to the sawtooth generator for frequency elements control in the horizontal deflection plates one side, and another side we are giving the magnitude information, that is by using the mixer stage. Okay. As the oscillator sweeps from F minimum to F maximum, so the oscillator sweeps the minimum frequency range to maximum frequency range of its frequency band at the linear recurring rate. It beats with the frequency component of the input signal and produces an IF. So it is comparing with the input signal, and it will mix with the input signal, and it will give an output of intermediate frequency range of the signals. Whenever a frequency component is met during its sweep, so the frequency component will be which will be mixed with the sweep or sawtooth generator. The frequency component and voltage tuned oscillator frequency beats together to produce a different frequency, that is IF. The IF corresponding to the component is amplified and detected if necessary, and then applied to the vertical plates of the CRO, producing a display and amplitude versus frequency. Finally, the amplified signal we are giving to the vertical deflection plates, where sawtooth wave generator is connected to the horizontal plates. Finally, it will produce a graph which will be there amplitude versus frequency. So finally the display will provide amplitude with respect to the frequency parameters. So this is the basic spectrum analysis. This is the basic spectrum analyzer block diagram theoretical section. Okay, now coming to that, from the basic spectrum analyzer, we will get the outputs of these signals when the spectrum produced, if the input wave is a single toned AM, a single toned amplitude modulated when you have given, then you will get the outputs in this fashion. So here, the test wave seen in a ordinary CRO. First, if you want to see the output in a ordinary CRO, so this is an ordinary CRO section. In this ordinary CRO section, the amplitude information, the time information is available. Now coming to that, in the spectrum analyzer, this is the spectrum analyzer section. This is the spectrum analyzer section, where on the x-axis we have frequency, on the y-axis we have amplitude. So this is the graph you can see on the normal CRO. This is the graph you can see on the spectrum analyzer. So you can get some of the straight lines which is representing the sinusoidal information. And coming to here, the test wave as seen on x-axis and z-axis, that is time and frequency. If you are seeing the time and frequency, so see here, this is the frequency representing curve, this is the time representing curve. So this is the fundamental frequency, and this is the second harmonic signal based frequency response of the signal. On the both y direction we have the amplitude information, where x-axis we are differing one side time, one side frequency. So this is one more waveform which we will get from the spectrum analyzer. Okay, right. The same waveform explanation here we are giving. Now, one of the principal applications of the spectrum analyzer. So directly we are there going with a spectrum analyzer applications with RF band also. First we have covered up to now basic spectrum analyzer, then we will see after this slide RF spectrum analyzer. So one of the principal applications of the spectrum analyzer has been in the study of RF spectrum produced microwave instruments. Generally, RF spectrum analyzer which is used for microwave applications or microwave instruments. In a microwave instruments, the horizontal axis can display as a wide range of 2 to 3 gigahertz. The spectrum analyzer which is used for microwave applications, it will display nearly up to 3 gigahertz frequency based signals for a broad survey and as a narrow as 30 kilohertz. It should produce minimum 30 kilohertz frequency signals behavior and it should produce maximum of 3 gigahertz frequency range signals for a highly magnified view of any small portion of the spectrum. So whatever it may be signals you are going to see, we should produce a high magnitude of information as much as possible. Signals at microwave frequency separated by only a few kilohertz can be seen individually. Signals at the microwave frequency separated by only a few kilohertz can be individually. That is the normal information. Next, so see here, this is the RF spectrum analyzer. This is the RF spectrum analyzer. In this RF spectrum analyzer, see here, first here we have the input signal block. Here we have the input signal from 0 to 1 gigahertz. Generally, this is the RF based frequency range. In this RF frequency based range, the input 0 to 1 gigahertz is available. Then low pass filter. Right, here we have a low pass filter, then we have the mixer stage, then we have IF amplifier, next detector, next vertical deflection plates. So everything is normal as a basic amplifier. Next, here we have the sweep generator. In the place of sawtooth generator, we are taking sweep generator. Next, here we have voltage tuned local oscillator, which is ranging from 0 to 2 gigahertz, which is ranging from 0 to 2 to 3 gigahertz. 2 to 3 gigahertz range is there. Okay, right. So the input signal is less than 1 gigahertz. The voltage tuned oscillator has a running with 2 to 3 gigahertz. Now these two signals are mixed here. Then it is connected to the IF amplifier. Then we have the detector and video amplifier stage. Finally, we have the display section of the spectrum analyzer. So this is the basic view of RF spectrum analyzer. Right. The frequency range covered by this instrument from 1 megahertz to 40 gigahertz. It is covered from 1 megahertz to 40 gigahertz. A spectrum analyzer covering a range of 500 kilohertz to 1 kilohertz. A spectrum analyzer covering the range from 500 kilohertz to 1 gigahertz, which is representative of a super heterodyne type. So it has a receiver of super heterodyne type. A super heterodyne type receiver is ranging from 500 kHz to 1 GHz signals. The input signal is fed into a mixer which is driven by a local oscillator. The input signal is connected to the mixer stage with the help of local oscillator, which is driven by the local oscillator. This oscillator is linearly tunable electrically over the range of 2 to 3 GHz. Electrically, we can vary the frequency range from 2 to 3 GHz. The mixer provides two signals. At its output. They are proportional to the amplitude to the input signal, but of the frequencies which are the sum and difference of the input signal and local oscillator frequencies. Actually, at the stage of mixer output, we will get two types of output signals. There will be sum and differences of the signals. These two signals we are connecting to the next stages. The IF amplifier is tuned to a narrow band around 2 GHz since the local oscillator is tuned over the range of 2 to 3 GHz. Only inputs that are separated from the local oscillator frequency by 2 GHz will be converted to the IF frequency band, where below 2 GHz frequency signals only converted to the IF stage signals and passes through the IF frequency amplifier and get rectified and produced in the vertical deflection plate CRT, and those signals only displayed in that particular CRT. Okay, right. Next, coming to that, spectrum analyzers are widely used in radars, oceanograph and biomedical fields. So majorly these type of spectrum analyzers we are using in the biomedical applications and different types of radars and oceanographic applications. Okay, so this is about spectrum analyzers. In the next class, we will discuss digital Fourier analyzers.